Okay, so watch and listen carefully here, guys. So for question number 1, right, we got the catapult. Okay, and the catapult is shooting this rock at an impressive speed of 29 meters per second. Okay, if the catapult was drawn back 3 meters, how much force was used? So first mark is for their givens. Okay, we know the mass of the rock is 50 kilograms. Okay, we know the speed of the rock is 29 meters per second, or probably the final speed of the rock is 29 meters per second, because we can assume that while it is sitting in the catapult, its speed is 0. Okay, they don't have to have written that, but that's fine if they did. All right, and lastly, we know the distance that the catapult was pulled back was 3 meters. 1 mark for that. Okay, next mark. Work is a change in energy. All right, we talked about yesterday how you can tell whether a question is a law of conservation of energy question or a work energy theorem question, and that is one of the dead giveaways. Any question asking or giving force is a work question. All right, so work is a change in energy. Give them a mark for that, or maybe they went straight to this. Force times distance is EF minus EI, okay, or something along those lines. Maybe they went straight to this as well. FD equals 1/2 MVF squared minus 1/2 MVI squared. Okay, any of those are good for that mark, but I will give a second mark if they have this. Sorry, a third mark if they have that, because that's essentially what this comes down to. There is no initial energy, so the work done is equal to the final kinetic energy of the rock. Everybody follow me there? Okay, we're manipulating here to find the force, so what do I have to do with D? Divide both sides by it, so I end up with this. F equals 1/2 MVF squared over D. Okay, or maybe they went straight to plugging in the numbers and they have 1/2 times 50 times 29 squared over 3. Okay, if they have either one of those things, that's their 4th mark. And their last mark. The force comes out to 7,008.3. They don't have to have had the 0.3. If they wrote 7,008, that's fine. Newtons. They do have to have newtons as the units, however. If they don't, it's not right. Okay, questions on that one? I will let you know that I made that question up about the same time I made up the one of the work energy theorem questions on your test. About the same time. Okay, number 2. So we got this little rocket that, unfortunately, in the end, I picked bad numbers and doesn't go very high, but whatever. Okay, so we've got this 0.250 kilogram rocket. So we know the mass. Okay, we know the force exerted on it is 200 newtons. Okay, and that force was exerted over 4.5 meters. Okay, 1 mark for their givens. All right, again, this has one of the dead giveaways. A force was given, so it is a work energy theorem question. Okay, or they may have had force times distance equals EPF minus EPI. Okay, or force times distance equals MGHF minus MGHI. Okay, anything along those lines. All right. I will give a 3rd mark if, again, they realize that that was 0. Okay, and they have that. Force times distance equals MGHI. Something along those lines. Sorry, MGHF, sorry. All right, we're looking for how high the rocket goes. Which of these terms is that? HF. All right, so we're looking. Whoop, thank you, Brad. We're looking for HF, so I have to divide both sides by mg to get it by itself. Okay, so if they have this manipulation, HF equals FD over mg, or maybe they went straight to plugging in the numbers, so they have 200 newtons times 4.5 meters, okay, and over 0.25 times 9.81. And I think I punched that into my calculator wrong, so we'll just double check my answer that I have written down here. Okay, so we have 200 times 4.5, okay, divided by 0.25 times 9.81. Good thing I double checked, because that's a lot bigger than the number I got. Okay, so 367 or 366, yeah, it's 367, we'll say. 367 meters, okay, as their fifth and final mark. Okay, give them a mark out of 10. Let them see it. Put it in the box, please. All right, so yesterday we got to this point. All right, this point here we were talking about work done, and these were all basically work energy theorem questions here in question number 5, right? Calculating the work done and compressing the spring was force times distance, and you got 4 joules, okay? If the spring is released, what happens to the energy of the spring? What will it do? Okay, it'll turn the potential energy into kinetic. Whenever an energy conversion goes on, there has to be what done? Work. Because usually when you're converting energy, you're also changing it, transferring it, okay, something along those lines. So you're doing work, okay. So it'll do work on the ball. Okay, calculate the energy of the ball the instant it leaves the spring. Do you really need to calculate that, or should we just know what it is? We should just know, because we calculated the work done, and we should know. The work energy theorem says that once you put energy in a system by doing work, that's all the energy the system will ever have. Okay. For part E, okay, what we do is we say that, all right, it'll have 4 joules of kinetic energy, so we set 4 joules, okay, equal to 1/2 mv squared, and we solve for V. Okay, and when we do that, we get 28.3. All right, and then it asks us again, and this is the same stuff we went over in class yesterday, what's the gravitational potential energy the ball will gain? Well, if it had 4 joules of kinetic energy worth of, had 4 joules of kinetic energy when it left the ground, it can never have more than 4 joules of mechanical energy in total, can it? So when it gets to its maximum height, those 4 joules are all in what form? Kinetic, potential, right? Okay, it still has 4 joules of mechanical energy, it's just all potential at that point. So you set 4 joules equal to mgh, just like we did in the questions on the quiz today. All right, and then you would solve for h, which ended up being 40.8 meters. Now for number 6, you got the 60 kilogram athlete who jumps vertically upward from the ground to a height of 0.910 meters. What's the athlete's initial vertical speed? Okay, now this one is a little bit trickier. All right, so for number 6, is it a work energy theorem question or is it a law of conservation of energy question? How many people didn't get to number 6 yesterday? Okay, that would be why no one knows. Okay. Do they give me anything about force or distance here? No. So is it a work energy theorem question? No. Okay. This question is asking me to compare 2 different places in the same system. All right, so 2 different positions in the same system. When he's standing on the ground, if he's going to propel himself into the air, what kind of energy does he have to have? Kinetic. Okay? There's no way he's going to have any gravitational potential energy if he doesn't have any kinetic energy when he leaves the ground, because he'll have nothing to convert into potential energy. You guys follow me there? Okay? So, if there's no work being done, is the energy on the ground equal to the energy when he's at 0.910 meters? Yes. All right? And that's what we talked about yesterday. Questions where the initial mechanical energy equals the final mechanical energy. All right. On the ground, does he have any potential energy? No. All right. So let's set this up like we did yesterday. We have the initial energy could mean, the initial mechanical means initial potential plus initial kinetic equals final potential plus final kinetic. All right. Remember that yesterday we talked about mechanical energy as the sum of the 2 kinds of energy. Is that ringing a bell for everybody? Okay. If we want to calculate mechanical, we add them together. So the mechanical at the beginning is equal to the mechanical energy at the end. At the beginning, since he's on the ground, this is 0. At the end, when he's at his maximum height, which one of these is 0? The kinetic, because he's not moving. All right, because he jumped straight up in the air. All right, do I have a formula for kinetic energy? Okay, 1/2 mvi squared. Formula for potential? mgh. All right. They told me he reaches a height of 0.910 meters. That's HF. Okay. They told me his mass, 60 kilograms, even though it won't matter. Okay. And do I know G? I always know G. All right. I'm asked to find what was the initial vertical speed. So VI. How do I solve for VI? Divide by half m. And square root. Okay, does that look familiar? We did a couple of those yesterday. Alright, so if I want to calculate what that is, I'll have 9.81 times 0.91 over 1/2. Okay, so when we plug in that into our calculator, okay, we should get 4.23 meters per second. All right, everybody follow what I did there? Okay, so like I said, we did a few of those yesterday, but probably have forgotten a little bit of it. Okay, let's have you guys try number 7. Okay, I know you have the whole question on your sheet. Okay, so I'm just gonna fix this so I have all of it as well. Okay, and then we'll go over it in a few minutes here. So let's have a look at 7 here. Okay, so we got this 0.30 kilogram billiard ball propelled from a table at a horizontal speed of 1.5 meters per second. The table's 1.30 meters above the floor. We want to find the mechanical energy of the ball. So, does it have potential energy? Okay, does it have kinetic energy? Yes. All right, it does because it's 1.30 meters above the floor when it leaves the table, right? So it has both. All right, well, mechanical energy is the sum of an object's potential and an object's kinetic energy. So all we have to do here is go m times g times h plus 1/2 mv squared. All right, so we've got 0.3 kilograms times 9.81 times 1.3 plus 1/2 times 0.3 times 1.5 squared. All right, so when we punch that in, all right, we should have, has to be on. All right, 4.16 joules. Okay, questions on that one? All right. Now, I'm going to move on here to a different type of question. Here is your typical law of conservation of energy question. I have a roller coaster. Let's say it's, I don't know, 1,600 kilograms, including riders, which I didn't draw. And it's still on the track, even though it doesn't look like it. Okay. Alright, so up here the roller coaster is moving at about 5 meters per second. It's 50 meters off the ground. Down here it's only 8 meters off the ground. And I want to find out how fast it's going. Okay? Is there any work being done in this question? No. All right. The cart on the roller coaster. The roller coaster cart is simply going to go down the hill and then up the little bump there. All right. That's all that's going to happen in this question. There's no forces doing any work here. All right. The work has already been done in bringing the roller coaster trolley to the top of the first hill. Okay. So if there's no work being done, is the energy at the top of the hill equal to the energy on the little hill? Yes. All right. The only thing that's different is its distribution. Here at the top of the tall hill, most of the energy is in what form? Potential. There's some kinetic, but there's mostly potential. Okay? Down here, most of the energy will be kinetic. It'll be moving a lot faster here, agreed? Okay. So that's what we want to find here is how fast the roller coaster is going at the bottom. All right. So we've already said the mechanical energy, at least, is the same top and bottom. EI equals EF. Okay. Now, we've also said that it has both kinds at the beginning. Initial kinetic and initial potential. And it has both kinds at the end. Everyone okay with that so far? Okay. Do I have formulas for each of those terms? Okay. So 1/2 mvf squared, or sorry, that's the I side, sorry. Okay, have I said basically the same thing in the first three things I've written there? Yeah, right, I'm saying exactly the same thing. I'm just expanding the terms out, okay, to include more stuff. All right, I want to solve for what here? The final speed. So if I want to get VF all by itself, what do I need to do first? Nope, I can't divide yet. I have an addition operation that is going on that side. Right, I have to subtract it. Is this very much like what we did yesterday when they said, here's the mechanical energy, here's the kinetic energy, find the potential, and then we'd subtract the one we knew? Okay, that's exactly what we're doing here. That's why we did that stuff yesterday. It's kind of the baby steps we would use to get to this point. I want to solve for something that's part of final kinetic energy, which means I need to subtract the final potential from the mechanical, this part, okay, to find out how much kinetic energy there is. That's why I do the subtraction operation first. Okay, so everyone follow my reasoning there? Okay, all right. So the next step then is that I have 1/2 mvi squared plus mghi minus mghf equals 1/2 mvf squared. All right, math trick. What is in every one of those terms? Mass. If I'm multiplying each and every term in that equation by the same number, can I make that number 1? Yes. That means I can cancel m. All right? I don't have to use 1600 in there for m. I can just cancel it. I'm multiplying every single number by it. All right? If you're not comfortable with doing that, you don't have to. You can leave mass in there and it won't make any difference. Okay? It'll cancel itself off. But I like to have less things to write, so I'm getting rid of it. Mass is gone. I want VF by itself, so what do I have to move now? The 1/2. How do I move the 1/2 now? Divide. Right, divide by 1/2. All right, that gives me VF squared. Square root. Okay, not a lot different than the the high jumper question or things like that. Okay. It's just we got all the kinds of energy. So now we've manipulated. Okay, our final formula looks something like this. Okay, we'll have the square root of 1/2 of VI squared, or if you left the m's in, MVI squared, plus GHI minus GHF over 1/2. The 1/2s do not cancel. Okay. The reason they do not cancel is because I've got, again, this operation having to be done first before I divide by 1/2. Okay? All right, that equals VF. Okay, if I plug in my numbers, then it looks like this. 1/2 times 5 squared plus 9.81 times 50 minus 9.81 times 8 over 1/2. Okay, so this 5 here was the initial velocity, this 50 was the initial height, this 8 was the final height. All right, now I can plug it into my calculator. Okay, should you do this one with lots of brackets and the square root all at one time, or should you do it one piece at a time? I would suggest one piece at a time. Okay, again, in the end, if you had all of this work all shown on a test or something like that and you decided to take a chance, you'd only lose 1 mark for not getting the answer right. Okay, but I like to get all the marks if I can. So 0.5 times 5 squared, okay, gives me that. All right, plus 9.81 times 50. All right, minus 9.81 times 8. Gives me that, divided by 0.5. Gives me that. Square root of that gives me a speed of 29.1 meters per second at the top of the 8-meter hill. that is as hard as they get. Okay? There is no way for me to ask you a harder law of conservation of energy question in grade 10 science. That's as hard as they get. All right? You guys kind of follow what I did there. All right? It's a lot of algebra. I won't lie to you. It's a lot of algebra. All right? But in the end, as long as you understand that mechanical energy doesn't change, I think you can all get to the point where you would figure it out. All right? Okay. Okay. What I would like you to do now is at the bottom of the Science 10 Work and Energy worksheet you got the other day, okay? There is section 4, Conservation of Mechanical Energy questions, okay? Numbers 14 through 17 that are just like this question here. Okay. Need to call? Need to call home? Do you need to go call home? You sure? Okay. So I'd like you to try those 4 questions, and then we'll go through them together, and then I'll put a couple more examples up for you. Okay, so on number 14, again, with any type of law of conservation of energy question, your first chore is that you need to identify the types of energy present initially and finally. Okay, because we know in a law of conservation of energy question that the initial mechanical energy is equal to the final mechanical energy. How do we know that that's true in this question? Are we ever given force or distance? And the word work is never mentioned either. All right, so it is definitely a situation where whatever energy the person has when they leave the ground, in this case, is the energy they will have when going over the bar. Okay, you guys follow me there? All right. So if you are on the ground in pole vault, okay, so you come in, you plant the pole bends, okay, you are still on the ground. All of your energy at that point is kinetic, okay? And the whole object of pole vault is to convert the kinetic energy of your run-up into potential energy as you go up and over the bar. All right, now, some of that has to do with your speed, and a lot of it has to do with your technique. But let's just say, to simplify for physics' sake, it has entirely nothing to do with anything but your speed. Okay? So if you can run really fast, you can jump over the bar. It isn't that easy, but we'll say it is. Okay? So initially, okay, EPI plus EKI equals EPF plus EKF. All right? Now we just finished saying that initially, since they're on the ground, they don't have any of that. All right? And as they go over their bar, they would only have potential. Okay? We're going to assume that they go straight up in the air. We're simplifying everything here. Okay? So they would have no kinetic energy as they go over the bar. All right. Do I have a formula for kinetic energy? Yes. 1/2 mv squared equals the formula for potential energy, mgh. And this is F, and that's I. All right. Let's go back here to something we probably should have done first. Givens. Initial velocity, 9.0 meters per second. Okay, and that's it. So all we're given. We know G. G is 9.81. Okay. Why don't I have to give you the mass of the pole vaulter? Okay. Yeah, to some extent it's that, but also because mathematically it's going to cancel. All right, here's, guys, what I've done in the past. I won't be this cruel. Well, I shouldn't say that. I might be. Depends what kind of mood I'm in. Okay, on the test, I sometimes don't give the mass on the law of conservation of energy question. And people come up and they ask me, Mr. Coder, don't I need the mass for this question? Let's say it's a roller coaster. First person who comes up, I say, oh, I forgot. It's 500 kilograms. And they're happy and they go and sit down. And then another person who wasn't listening comes up and, Mr. Coder, I think I need the mass for this question. Oh, yeah, I forgot. It's 200,000 kilograms. And then people start looking, and they're, what's going on here? He told the first person it was 500. He told the second person it was 200,000. The third person comes up. What's the mass? 2 kilograms. Oh my God, I don't know what to do. He's messing with us, and I am messing with you because you don't need the mass. in a law of conservation of energy question that doesn't ask for energy. All right. So yeah, I have done that in the past. I probably won't. Usually now I just write a mass on there, and if you use it, you use it, and if you don't, you don't. But I've actually done that once. No, I already put the mass on the test. The question on the test already has the mass in it, so you can use it or not. If you recognize you don't need it, you don't need it. Okay? All right, anyway, back to this. We're trying to find out how high the person can go, assuming only their kinetic energy / speed determines how high they will go. So, how do I get HF by itself, Brooklyn? Who wanted to know how this question was going but was looking at her phone? What do? I don't subtract, I divide, right? Mg. Okay, here's where our m's cancel. M is gone. All right. Now I can find HF. I don't have to square root or anything because HF isn't squared. All right, I just plug in my numbers. 1/2 times 9 squared over 9.81. Okay, so, and the answer is on there, right? 4.12 meters. Which is a very respectable high school pole vault number. Okay. Does everyone follow how that one worked? Okay, guys, any law of conservation of energy question, you want to start with those two steps. Okay, EI equals EF, write down all 4 forms of energy that are possible, and cross off any ones that happen to be 0. In some questions, 1 might be 0. In some questions, 2 of them might be 0. That's the most. Okay, you can't ever have 3 that would be 0, otherwise an entire side would be 0, and then you have no energy. Okay, but it's possible that you could have a question with 2 or 1 of them being 0. Okay, all right, keep going there, guys. So we've got this 2-kilogram rock released from a height of 20 meters. If it is released from a height of 20 meters, what kind of energy did it have at 20 meters? Potential only. All right. Okay. So it says ignore air resistance and can determine the kinetic energy, gravitational energy, and total mechanical energy at each of the following heights. All right. What do we know about this number here? It stays the same. All right. It can never have more mechanical energy than it had at the beginning because there's nothing doing any work on it as it falls. Agreed? Okay. So initially, okay, so what we've got here is we'll say 20 meters, okay, 15 meters, 10 meters, and 0 meters. Okay, we'll do something like this. All right, and right across the top here, we'll have EP, EK, EM. All right, if I want to calculate the potential energy at 20 meters, how do I do that? MGH. Okay, and that's going to be easy because I can already fill this one in. It's 0. If I released it, it wasn't moving. All right, so I already know that EK at that point is 0. So EP at this point is going to be M times G times H. All right, so that'll be, for this one here, 2-kilogram rock. Okay, so 2 times 9, 2 times 9.81, okay, times 20 meters. All right, 392.4 joules. 392.4 joules. 392.4 joules. 392.4 joules. 392.4 joules. Okay? That number does not change. All right. Can I find the potential energy at all of those heights? Okay? That's probably the easiest one to find, right? Okay. Because they never tell me the speed. I can't use 1/2 mv squared for any of these heights to find EK, can I? But what I have to understand is, if I know EP and the total, what do I have to do to get EK? Subtract. Okay? Then I just fill in the blanks down here. That's all I do all the way along. All right, so for the 15-meter one, 2 times 9.81 times 15. Okay, 294.3. Whoop, 0.3. Okay, and then again, okay, 19.62 times 10. Okay, so 196.2 joules, joules, 0 joules, 392.4 joules. Okay, and then I just do the subtracting here. So this should be, was it 96.2? 196. Yeah, right, so that's where they're equal. 196.2, and then here, this one should be 98.1. Yeah, 98.1. Joules, joules. Yeah. Okay, does that make sense to everybody? All right. So the big thing that question was asking wasn't that you could subtract. Okay, that question was asking, did you understand that the mechanical energy never changes? Okay. All right, I'll give you a few more minutes there to try number 16. Okay, so on number 16 here, we got the person going down this hill on a sled. The hill is 4.6 meters tall. Okay, so it's 4.6 meters tall. They start at the top with a speed of 3.1. Okay. Meters per second, and we want to know what the speed is down here when the sled is at the bottom of the hill. All right, what's the height down here? 0. Okay. Energy the same top and bottom? Yes. All right. EI equals EF. How do I know the energy is the same top and bottom? There's no mention of work or forces or distance anywhere in this question, is there? Okay. At the beginning, they're moving, so they have kinetic energy. They're also 4.6 meters above the bottom of the hill, so they also have potential energy. At the end, they have a height of 0. They have no potential energy, but they're probably moving pretty fast. Agreed? Okay, so they have EKF. All right, let's put in the formulas. 1/2 mvi squared plus m times g times hi equals 1/2 mvf squared. Everybody okay with that so far? All right, how do I get VF by itself? Okay, what can I do with all the m's? I can cancel them out, right? Which is good, because I didn't give you the mass in that question. Okay, the reason I didn't give you the mass, you didn't need it. All right, it cancels off anyway. All right, so now, divide both sides by 1/2 and square root. Okay, so when we plug in our numbers there, 1/2 times 3.1 squared plus 9.81 times 4.6 over 1/2. Okay, 9.99 rounds to 10. Okay, meters per second at the bottom of the hill. Okay, are all these working pretty much the same way? Okay, the formula, guys, the recipe for doing these questions is exactly the same each and every time. All right, so if you don't see force, distance, or work, EI equals EF. Write in the forms of energy where they are. Manipulate for what it is you're looking for. It's exactly the same each time. All right, give the last one a try there. Okay, hopefully we'll be able to go through it before the end of class. Okay, so let's quickly have a look at 17 here before the bell goes. So this woman runs off of a diving board, or a diving platform, which is essentially like running off a cliff, okay, at 5.4 meters per second. It's a 10-meter diving platform, so the standard high diving platform. Okay, we want to figure out how fast she's going when she splashes down, okay, into the water. Is this pretty much the same as the last question? In fact, other than the numbers being different, the method is exactly the same. All right, she has no potential energy when she strikes the water because that's a height of 0. Okay, she has both potential and kinetic here at the beginning. All right, so EI equals EF. Okay, so we'll have our 1/2 MVI squared plus MGHI equals 1/2 MVF squared. We won't bother writing MGHF because it was 0 anyway. Okay, we're manipulating for VF. The M's all cancel. Okay, we divide by 1/2 and we square root. Okay, when we plug in our numbers, we should get 15.01 meters per second. Okay, we will probably have some more time on Thursday to work on a few more problems like this because efficiency won't take me very long to teach you. Okay, tomorrow we are going to be doing a lab on conversions of energy. Friday review, Monday test. MJ. No, the halves will not cancel. Right, because this is calculating essentially the mechanical energy. Right? Half times VI. Yep, 0.5 times VI, yep. Middle of next week. Yeah, you got tests and stuff, so.